Today we're going to look at how to calculate the pH of a buffer solution. So we're going to look at the mathematical method that can be used to do this. Alright, so let's have a look at an example question. You might want to have a look at this and see if you can solve it yourself before I explain how to get the answer. So here's our question. We've got a buffer solution and it contains a mixture of 30 grams of ethanoic acid, CH3COOH, and 82 grams of sodium ethanoate, CH3COONA. And these have been mixed and then dissolved in 500 centimetres cubed of solution. So we know that this is a buffer solution because we've got both a substantial amount of the salt of the weak acid as well as the weak acid itself. We've also got the Ka of our weak acid in this particular question, and you should be able to write out the Ka expression for our weak acid. So that's the products of the acid-base equilibrium on the top divided by the concentration of the weak acid, which is, if you like, the reagent on the bottom. So on the top you've got your proton concentration multiplied by your salt of your weak acid concentration and then divided by your weak acid concentration. Lovely. So step one in our calculation is to read the question carefully and see if we can calculate the moles of our weak acid and our salt of our weak acid. We're going to have to do this because we've been given masses. We haven't been given a nice straightforward question where we've already got our concentrations. We're going to have to deduce that for ourselves. So to work out the concentration of our weak acid, we need to first work out the moles of it. So to do that, mass divided by mR, and then to convert that to a concentration, you divide it by the volume in decimeters cubed. So our weak acid conc is 1 mole per decimeter cubed, and similarly for our salt, again mass divided by mR, giving you your moles, divide that by the volume in decimeters cubed, which is 0.5, and we get a concentration for our salt of 2 moles per decimeter cubed. So these are both our initial concentrations of our weak acid and the salt of our weak acid, sodium ethanoate. Okay, so we have to, in any buffer solution calculation, make a couple of key assumptions. The first one is that the salt of the weak acid all dissociates in solution. So if you like, you have an irreversible reaction where 100% of your salt, in this case sodium ethanoate, makes the ethanoate anion, CH3COO- and sodium ions in solution. And we should also assume that all our weak acid molecules don't dissociate, so they stay as CH3COOH. If you like, your initial concentration is the same as your equilibrium concentration of your weak acid. And that does tie in with the definition of a weak acid, in the sense that equilibria for weak acid lies far to the left, rather than in the case of a strong acid like HCl, where the equilibria lies all the way over to the right. You get that, you can see that by just looking at the Ka there. It's 1.74 times 10 to the minus 5, far over to the left, a lot less than 1. Alright, so using those two assumptions, we can now get on and work out our H plus concentration, which is, after all, what we need to work out to derive the pH. So we can substitute into our Ka expression all the numbers that we know. We've got our Ka value, which we were told in the question, 1.74 times 10 to the minus 5 moles per decimeter cubed. We don't know our proton concentration, That's our unknown. But we do know the concentration of our ethanoate ion and also the concentration of our weak acids at equilibria. Sub them all in, rearrange the equation to make H plus, your concentration of H plus the subject, plug it into your calculator, and you should get an H plus concentration of 8.7 times 10 to the minus 6, that's 8.70. Don't round up too much as you go through the actual calculation. Store the values on your calculator. Only round up for the final answer when we derive the pH by doing the minus log of our proton concentration. So pH is equal to the minus log of 8.7 times 10 to the minus 6 in this case, which will give you a pH of 5.06 to 3 sig figs. And that's an appropriate number, because if you look at all the data in the question, the least accurate data is 3 sig figs. Cool. Okay, so in summary, the general method to do any of these calculations is to, if you like, first read the question or derive your concentration of your salt of your weak acid and your concentration of your weak acid. So you'll need to carefully read the question to get some concentration values, whatever they may be, okay, for your known concentration values. You'd need to apply the assumptions that we use when doing buffer calculations, and that is that your weak acid doesn't dissociate much, so therefore, well, at all, that your equilibrium concentration of your weak acid is pretty much the same as all the initial. And we can also assume that your salt will 100% dissociate to make the the salt ions. You would then substitute them into your Ka expression, rearrange to find your proton concentration, and then to do pH, you would just do the minus log of that proton concentration. And there you go, job's a good one. The same principle could be applied to find any one of the unknowns in your Ka expression, as long as you know all the other three values. So, for example, you could find the Ka if you knew the pH, and you could work out the concentration of the salt and the weak acid, for example. All right.